Picture this: you're looking up at the night sky, but what you see is just a tiny fraction of what's actually out there. The stars, the galaxies, even the vast emptiness between them. It's all just the visible tip of an enormous cosmic iceberg. The truth is, 85% of the universe's mass is missing. It's not hiding, it's simply invisible to us. So where is it? What exactly is this ghostly, unseen force shaping the cosmos? Scientists call it dark matter and dark energy, two of the biggest mysteries in modern physics. They bend light, dictate how galaxies move, and even control the fate of the universe itself, yet we still don't fully understand what they are. But that's where things get exciting. Today, we're diving deep into 30 mind-bending theories that could finally crack this cosmic code. From invisible particles to hidden dimensions, alternate realities to the very fabric of space-time, these ideas stretch the limits of our imagination. So if you're ready to explore the greatest unsolved puzzle of the universe, let's begin. Now, let's start peeling back the layers of this cosmic mystery with the leading explanation: cold dark matter. Imagine a universe where most of the matter isn't made of atoms, stars, or planets. Instead, it's an invisible sea of particles that barely interact with light or ordinary matter. That's the heart of the cold dark matter theory, the frontrunner in the hunt for the universe's missing mass. At the core of this idea are weakly interacting massive particles, or WIMP. These hypothetical particles are thought to be heavy, slow-moving, and extraordinarily shy. They rarely bump into the matter we know, which is why we can't see or feel them. But their gravity, that's a different story. WIMP may be invisible, but their gravitational pull is powerful enough to sculpt galaxies and bend the fabric of space itself. One of the strongest clues supporting cold dark matter comes from something called galactic rotation curves. Here's how it works. When astronomers measure how fast stars orbit the center of a galaxy, they expect stars on the outskirts to move slower, just like planets farther from the sun. But that's not what happens. Stars at the edge of galaxies whip around just as fast as those near the middle, as if some unseen mass is holding them in place. Cold dark matter provides the missing glue, an invisible halo of WIMP enveloping galaxies, adding the extra gravity needed to explain these odd speeds. But cold dark matter doesn't just explain galactic motions. It's also a master architect of the universe's large-scale structure. Simulations show that without cold dark matter's gravitational scaffolding, galaxies wouldn't have formed the vast cosmic webs we see today. Tiny fluctuations in the early universe were amplified by dark matter's pull, creating dense regions where ordinary matter could eventually clump into stars and galaxies. Still, the theory isn't flawless. For decades, scientists have searched for direct evidence of WIMP in underground labs, where sensitive detectors wait for the rare moment a dark matter particle might collide with an atom. So far, no definitive signal has appeared, leaving room for rival theories. But cold dark matter remains the most robust framework we have, a ghostly backbone holding the cosmos together, even if we're still learning how to see it. Up next, we'll explore a bold challenge to this idea, a theory that doesn't rely on invisible particles at all, but rewrites the rules of gravity itself. Now, let's shift gears to a theory that flips the script entirely. What if the missing mass isn't made of invisible particles at all, but instead, our understanding of gravity is simply incomplete? Enter modified Newtonian dynamics, or MOND, a radical alternative that challenges the very foundation of cold dark matter. Instead of invoking mysterious particles, MOND proposes that gravity doesn't always follow Newton's or Einstein's rules, especially in the faint, sprawling outskirts of galaxies where accelerations are incredibly weak. The heart of MOND lies in a simple but bold tweak. When the gravitational pull becomes vanishingly small, like at the edges of galaxies, the force of gravity strengthens slightly, just enough to explain why stars orbit faster than expected. It's as if the universe has a hidden rulebook for low-energy environments, one that Newton never got to see. This tweak isn't arbitrary, though. MOND predictions match the rotation curves of many galaxies with startling precision, often better than cold dark matter simulations. For some galaxies, you don't need dark matter halos at all. Just a slight adjustment to gravity, and the math works out perfectly. One of MOND's biggest triumphs came with dwarf galaxies, tiny cosmic neighborhoods where dark matter models sometimes struggle to explain the observed motions of stars. MOND, however, nails these predictions with little fuss. It's as if these faint galaxies are whispering that gravity might indeed play by different rules in the cosmic quiet. Supporters argue that MOND eliminates the need for an invisible, undetected substance, offering a cleaner, more straightforward solution to the missing mass problem, at least on galactic scales. But here's where MOND hits a snag: the larger cosmic stage. When we zoom out to galaxy clusters or the sweeping filaments of the cosmic web, MOND predictions start to wobble. These colossal structures seem to require far more mass than MOND can account for, forcing its proponents to reintroduce, ironically, some form of unseen matter, albeit less than cold dark matter demands. Then there's the bullet cluster, a cosmic collision where the visible matter and the gravitational lensing effects appear to have separated, as if the gravity were tied to something invisible. Cold dark matter explains this neatly, but MOND struggles without additional assumptions. Another hurdle is relativity. Newton's laws work beautifully for everyday gravity, but Einstein's general relativity takes over when things get extreme, like near black holes or in the expanding universe. MOND's original formula was purely empirical, a patch for Newtonian physics, not a relativistic theory. Later attempts to craft a relativistic version, like tensor vector scalar gravity, have had mixed success, leaving some gaps in explaining phenomena like gravitational waves or the universe's large-scale geometry. So where does this leave us? MOND is a brilliant reminder that science thrives on questioning assumptions. It forces us to ask, are we missing particles, or are we missing something fundamental about gravity itself? While it might not replace dark matter entirely, MOND's successes hint that the truth could lie somewhere in between, a blend of revised gravity and unseen matter. It's a debate that keeps cosmologists on their toes, proving that even our best theories are works in progress. Up next, we'll turn to another dark matter contender, one that's lighter, faster, and could solve mysteries MOND and cold dark matter can't touch. Now, let's explore a middle ground between the heavy, slow-moving particles of cold dark matter and the gravity-altering approach of MOND warm dark matter. Imagine if the universe's missing mass wasn't made of sluggish giants but lighter, speedier particles like sterile neutrinos, zipping through space just fast enough to leave a distinct cosmic fingerprint. This is the heart of warm dark matter, a compelling twist on the dark matter saga that could solve some of the most stubborn puzzles in the cosmos. Unlike their cold dark matter cousins, warm dark matter particles are lighter and move more briskly, giving them a unique effect on the universe's structure. Picture a crowded room where cold dark matter behaves like people standing still, clumping together easily to form dense groups, while warm dark matter is like folks strolling around, smoothing out the crowd into a more even distribution. This subtle difference might explain why cold dark matter simulations often predict an overabundance of small satellite galaxies around larger ones, a problem warm dark matter neatly sidesteps. Those lighter particles, thanks to their higher speeds, would resist clumping too tightly, leaving fewer tiny galaxies in their wake. One of the leading candidates for warm dark matter is the sterile neutrino, a hypothetical cousin to the ordinary neutrinos we already know. These particles would interact even less with normal matter, making them nearly invisible, yet their slight mass and faster movement could sculpt the cosmos in ways that fit observations better. For instance, warm dark matter's smoothing effect might explain why we don't see as many dwarf galaxies as cold dark matter predicts, or why some galaxies have surprisingly sparse centers. It's as if the universe prefers a gentler touch when building its smaller structures. But warm dark matter isn't without its challenges. While it excels at explaining small-scale quirks, it struggles to match the sheer gravitational heft needed to hold together massive galaxy clusters or the sprawling cosmic web. There's also the question of detection. Sterile neutrinos, if they exist, are notoriously elusive. Experiments hunting for them rely on spotting faint X-ray signatures, hints of their decay, but so far the evidence remains tantalizingly indirect. What makes this theory fascinating is its potential to bridge gaps between competing ideas. Warm dark matter could offer a Goldilocks solution, not too fast, not too slow, blending the strengths of cold dark matter's large-scale success with a fix for its small-scale shortcomings. It's a reminder that the universe's missing mass might not come down to a single answer but a spectrum of possibilities, each leaving its mark on the cosmos in different ways. Up next, we'll turn to an even more elusive candidate particle so light and wispy, they blur the line between matter and wave. Now, let's shift our focus to one of the most intriguing candidates in the hunt for dark matter, actions. These ultralight particles, though still theoretical, pack a punch when it comes to solving not just one, but two major puzzles in physics. Picture this, a particle so tiny and elusive, it could be hiding in plain sight, weaving through the cosmos and shaping the universe in ways we're only beginning to understand. Actions didn't start as dark matter candidates. Their origins trace back to the world of quantum chromodynamics, the theory describing how quarks and gluons interact. In the late 1970s, physicists Roberto Pexi and Helen Quinn proposed actions as a solution to the strong CP problem, a perplexing quirk in particle physics. The puzzle revolves around why the strong nuclear force, which holds atomic nuclei together, doesn't seem to care about the difference between matter and antimatter in certain interactions. It's as if nature has a hidden symmetry we don't fully grasp, and actions emerged as the elegant fix. Here's where it gets fascinating. If actions exist, they wouldn't just solve the strong CP problem, they'd also be perfect candidates for dark matter. These particles are predicted to be incredibly light, possibly billions of times lighter than an electron, and they'd interact so weakly with ordinary matter that they'd be nearly invisible. Yet, their sheer numbers could add up to the gravitational bulk we've been searching for. Imagine a universe filled with an ocean of these ghostly particles, gently tugging at galaxies without ever making a sound. What makes actions particularly appealing is how they could form. In the early universe, as temperatures cooled, actions might have condensed out of the cosmic soup like dew on a leaf, creating a pervasive cold mist of particles. Unlike WIMP or sterile neutrinos, actions wouldn't rely on high-energy collisions to exist. They'd be born from the conditions of the universe itself. This makes them a natural fit for the cold, dark matter that seems to dominate galactic halos. But detecting actions is no small feat. Because they interact so feebly, traditional particle detectors are useless. Instead, scientists have gotten creative. Experiments like ADAM's Action Dark Matter experiment use powerful magnetic fields to coax actions into revealing themselves. The idea is that in the presence of a strong magnetic field, actions might convert into faint radio waves, a whisper in the static of the cosmos. It's like tuning an old-fashioned radio, searching for a station that no one's ever heard before. The stakes are high. If actions are found, they'd not only explain dark matter but also validate a key piece of quantum chromodynamics. It's a two-for-one deal that physicists dream about. Yet, the lack of definitive evidence keeps actions in the realm of tantalizing possibility. Some theories suggest actions could also explain other mysteries, like the unexpected transparency of the universe to certain high-energy light. As we move forward, the search for actions continues to push the boundaries of technology and ingenuity. Whether they're the answer to dark matter or another piece of the puzzle, one thing's certain: the universe loves to keep us guessing. Up next, we'll explore an even bolder idea: primordial black holes, ancient relics from the birth of the cosmos that might be hiding in plain sight. Now, let's turn our attention to a theory that takes us back to the very beginning: primordial black holes. These aren't your typical black holes born from collapsing stars. Instead, they could be ancient relics forged in the chaotic moments after the Big Bang. Imagine tiny, dense knots of space-time lurking unseen, their gravity weaving through the cosmos, possibly accounting for the missing mass we've been chasing. The idea of primordial black holes dates back to the work of Stephen Hawking and Bernard Carr in the 1970s. They theorized that in the early universe, extreme density fluctuations could have collapsed directly into black holes, bypassing the need for a star's death. These black holes could range wildly in size, from as small as an atom to as massive as a mountain. And here's the kicker: if enough of them exist, they could collectively make up dark matter. But how would we even spot something so elusive? One clue comes from microlensing. When a primordial black hole passes between us and a distant star, its gravity bends the star's light, causing a brief brightening. Astronomers have scanned millions of stars for these telltale flickers. So far, the results are mixed. While some events hint at invisible compact objects, the numbers don't quite add up to explain all of dark matter. It's like searching for shadows in a dim room. You catch glimpses, but the full picture stays out of reach. Then there's Hawking radiation, the slow evaporation of black holes predicted by Stephen Hawking. Smaller black holes would emit this radiation more intensely, eventually exploding in a burst of energy. If primordial black holes were abundant, we'd expect to see these fireworks in the cosmos. Yet the sky remains quiet, placing tight limits on how many tiny black holes could exist. It's a cosmic tug of war between theory and observation, with each new study narrowing the possibilities. Interestingly, primordial black holes could solve other puzzles too. Some scientists suggest they might be the seeds of supermassive black holes found at galaxy centers. Others speculate they could explain bizarre gravitational wave signals or even the mysterious planet 9 in our solar system. But until we catch one in the act, these remain tantalizing maybes. The hunt continues, with researchers refining their tools and expanding their searches. From gamma-ray telescopes scanning for Hawking radiation to next-generation microlensing surveys, every avenue brings us closer to answering whether these ancient ghosts are real. Whether they're the missing mass or just another piece of the puzzle, primordial black holes remind us that sometimes the most extraordinary answers lie in the universe's earliest moments. Next up, we'll dive into supersymmetry, a bold extension of particle physics that might hold the key to unlocking dark matter's identity. Shifting our gaze from the cosmic to the quantum, let's explore a theory that reimagines the very fabric of reality: supersymmetry, or SUSY for short. This elegant framework extends the standard model of particle physics by proposing a breathtaking symmetry. Every known particle has a hidden, heavier superpartner. These shadowy twins could be the missing pieces of the dark matter puzzle, lurking just beyond our current detectors. At its heart, supersymmetry is about balance. It suggests that for every Fermion particles like electrons and quarks that make up matter, there's a boson superpartner and vice versa. This symmetry isn't just mathematical poetry. It solves multiple cosmic riddles at once. For instance, it could explain why gravity is so weak compared to other forces, or why the Higgs boson is surprisingly lightweight. But most tantalizingly, the lightest superpartner, often the neutralino, would be stable, electrically neutral, and massive, a perfect dark matter candidate. Neutralinos are hypothetical particles blending traits of their superpartner parents: photons, Z bosons, and Higgs bosons. Their sheer mass, think hundreds to thousands of times heavier than a proton, means they'd clump gravitationally, sculpting galaxies just as dark matter does. Unlike WIMP, which interact weakly, neutralinos could annihilate each other, emitting gamma rays we might detect. Experiments like the Large Hadron Collider and space telescopes like Fermi have hunted these signals, but so far the evidence remains elusive. Critics argue that SUSY beauty might be its downfall. The theory initially predicted superpartners within reach of our colliders, yet none have appeared. Some physicists propose tweaks like split SUSY, where superpartners are outrageously heavy, but this stretches the theory's elegance. Others suggest we're simply missing subtle signatures in the data. It's a high-stakes waiting game. If SUSY is real, upgrading our detectors or refining analyzers could soon unveil it. Beyond dark matter, supersymmetry hints at deeper unification. It's a cornerstone of string theory, weaving space-time and quantum fields into a single tapestry. If proven, SUSY wouldn't just fill the mass gap, it'd rewrite our understanding of reality's building blocks. For now, it remains one of physics' most compelling what-ifs, a theory so powerful, we almost hope it's wrong because the alternative might be even stranger. Up next, we'll venture into mirror matter, a concept straight out of science fiction, where an entire shadow universe could be hiding in plain sight. Now let's step into a realm that feels like it's ripped straight from the pages of a sci-fi novel. Mirror matter. Imagine an entire universe identical to ours in structure but completely invisible, where every particle has a mirror counterpart. These shadow particles would interact with our world through just one fundamental force: gravity. That's the bold idea behind mirror matter theory, and it might just hold the key to dark matter's elusive nature. The concept is as simple as it is mind-bending. If mirror matter exists, it would explain why dark matter seems to permeate galaxies without emitting light or colliding with ordinary atoms. Picture it like a ghostly echo of our reality, occupying the same space but moving through it unseen. Every star, planet, or even human in our universe could have a mirror twin, imperceptibly sharing the cosmos with us. The only evidence of their presence would be the gravitational tug they exert on visible matter, exactly what we observe with dark matter. Where does this idea come from? It actually stems from symmetry, one of physics' most cherished principles. Just as your left and right hands are mirror images, the laws of nature might also have a hidden mirrored version. This symmetry could extend to particles, giving rise to a parallel sector governed by its own version of electromagnetism, strong and weak forces, but entirely decoupled from ours. The kicker: these mirror particles wouldn't just be passive observers. They could form mirror stars, mirror galaxies, even mirror life, all invisible to our telescopes. Critics raise a fair question: if mirror matter is everywhere, why haven't we detected it directly? The answer lies in its near-total isolation. Apart from gravity, mirror particles would barely interact with ours, making them extraordinarily hard to spot. Yet there are tantalizing hints. Some experiments, like neutron lifetime measurements, show odd discrepancies that could hint at particles decaying into the mirror realm. Even cosmic phenomena, like the unexpected brightness of certain supernova, might be explained by mirror matter interactions, but here's where it gets even wilder. If mirror matter exists, it could have shaped the universe in ways we're only beginning to grasp. For instance, mirror neutrinos might have influenced how galaxies clustered in the early cosmos. Or mirror black holes could be lurking undetected, warping spacetime without the usual stellar precursors. The possibilities are as vast as they are speculative, blending cutting-edge physics with cosmic mystery. Of course, mirror matter isn't without its challenges. For one, why is the mirror universe so perfectly dark? If it mirrored our universe exactly, we'd expect some overlap, some leakage between the two realms. Yet so far, no experiment has found definitive proof. Some theorists tweak the model, suggesting the mirror sector isn't identical but slightly different, maybe with heavier particles or altered forces. Others propose that mirror matter interacts via an undiscovered portal that occasionally bridges the two worlds, What makes this theory so compelling is its sheer audacity. It doesn't just add a new particle to the cosmic inventory, it proposes an entire shadow universe interlaced with our own. If proven, it would redefine not just dark matter but our place in the cosmos. Are we alone, or is there a mirror Earth out there, oblivious to our existence? For now, it remains one of physics' most poetic what-ifs. Next, we'll unravel how extra dimensions could hide dark matter in plain sight with Kaluza-Klein particles. Now let's venture into a theory that stretches the imagination literally. What if dark matter isn't missing at all, but hiding in dimensions beyond our own? Enter Kaluza-Klein particles, a fascinating idea rooted in string theory's extra dimensions. Picture our universe not as a three-dimensional stage, but as a multidimensional landscape where particles could have heavier, invisible counterparts lurking just out of sight. The story begins with a century-old insight. Back in the 1920s, physicists Theodore Kaluza and Oskar Klein proposed that electromagnetism and gravity could unite if our universe had an unseen fourth spatial dimension. Fast forward to today, and string theory takes this further, suggesting there could be up to 7 hidden dimensions, curled up so tightly that we never notice them. But here's the twist: particles moving through these dimensions wouldn't behave like ordinary matter. They'd appear to us as heavier, stable versions of known particles, Kaluza-Klein particles, and these could be the dark matter we've been searching for. How would this work? Imagine a guitar string vibrating at different frequencies to produce distinct musical notes. In string theory, particles are like those vibrations, and extra dimensions add new, notes, heavier versions of particles we know. A photon, for instance, could have a Kaluza-Klein twin with mass, making it a perfect dark matter candidate. Unlike ordinary photons, these heavy twins wouldn't interact with light, but their gravity would influence galaxies just as dark matter does. The beauty of this idea is how neatly it solves multiple puzzles. Kaluza-Klein particles would naturally be stable over cosmic timescales, unlike many short-lived theoretical particles. Their mass would stem from their momentum in the extra dimensions, explaining why they're heavy yet invisible. And because they're tied to fundamental forces, their abundance in the early universe could align perfectly with what we observe in dark matter's cosmic distribution. But how do we find something hiding in extra dimensions? Indirect clues might lie in high-energy particle collisions. If Kaluza-Klein particles exist, experiments like the Large Hadron Collider could, in theory, produce them fleetingly. Their decay signatures would be subtle, missing energy or unusual momentum patterns, but detectable. Meanwhile, astrophysical observations offer another angle. If these particles are dark matter, their annihilations in space could produce unique gamma-ray signals. Telescopes like Fermi are scanning the skies for such hints, though nothing definitive has emerged yet. Critics argue that extra dimensions, if they exist, might be too small or too energy-intensive to produce detectable Kaluza-Klein particles. Others point out that string theory itself remains unproven, making this a speculative leap. But supporters counter that dark matter's stubborn invisibility demands bold ideas. After all, if nature has extra dimensions, why wouldn't they play a role in one of the universe's greatest mysteries? What's thrilling is the scale of implication. If Kaluza-Klein particles are real, they'd do more than explain dark matter. They'd prove we're living in a higher dimensional universe with layers of reality folded beyond perception. It's a vision that merges the cosmic and the quantum, offering a bridge between the very large and the very small. Next, we'll challenge the notion of dark matter as a lone wanderer, exploring how it might interact with itself through a mysterious dark force. Stepping away from hidden dimensions, let's consider a radical twist on dark matter itself. What if it's not the solitary, ghostly presence we've assumed, but a bustling cosmic community with its own rules? This brings us to self-interacting dark matter, a theory that dares to rewrite the script on how dark matter behaves. For decades, the leading view painted dark matter as aloof, particles that barely notice each other, drifting through space without collisions. But observations of galaxy clusters threw a wrench in that idea. When clusters like the Bullet cluster collided, their dark matter seemed to lag behind the visible matter, almost as if it was experiencing some form of drag. If dark matter were truly collisionless, this behavior wouldn't make sense. That's where self-interacting dark matter steps in, proposing that these mysterious particles don't just pass through each other silently, they might interact through their own invisible force. Think of it like this: imagine two crowds passing through each other in a pitch-black room. Ordinary dark matter would act like phantoms, walking straight through without bumping shoulders. But self-interacting dark matter, that's like giving everyone in that room a subtle nudge, gentle enough that they still move freely, but with just enough friction to leave traces of their encounters. In cosmic terms, this nudge could explain why dark matter in colliding clusters behaves differently than expected. The math behind this idea is elegant. Physicists suggest that dark matter particles might exchange a hypothetical dark photon, a force carrier analogous to the photons that mediate light in our visible universe. These interactions would be rare enough to avoid collapsing dark matter halos into dense clumps, solving a key problem with earlier models, but frequent enough to leave fingerprints in violent cosmic events. Computer simulations show that self-interacting dark matter can reproduce the observed distributions of galaxies far better than the traditional collisionless model. But how do we test such an invisible handshake? One clue comes from dwarf galaxies. These small, faint galaxies orbiting our Milky Way should, in theory, host dense dark matter cores. Yet many appear to have surprisingly puffy distributions. Self-interacting dark matter could explain this by gently scattering particles outward over time, like a cosmic game of pool where the balls never sink into the pockets. Meanwhile, telescopes hunting for faint X-ray glows from possible dark matter interactions in galaxy clusters are adding pieces to the puzzle. Skeptics raise valid concerns. If dark matter interacts so weakly, why haven't we detected it in labs yet? Others argue that alternative solutions, like tweaks to galaxy formation models, could explain the same observations. But proponents counter that self-interacting dark matter offers a unifying framework, one that accounts for oddities across scales, from the tiniest galaxies to the largest clusters. What's captivating is the possibility of an entire dark sector, complete with its own forces and particles, operating alongside our familiar universe. It's not just about missing mass anymore. It's about uncovering a hidden cosmic society with its own set of rules. Next, we'll shift gears to an even stranger proposition: dark matter that isn't made of particles at all, but behaves like a wave enveloping the cosmos. Now imagine dark matter not as discrete particles nudging each other in the cosmic dark, but as an ethereal mist woven into the very fabric of space. Here's where fuzzy dark matter takes center stage, presenting a radically different vision of the universe's missing mass. Instead of bulky particles, this theory suggests dark matter could be made of unimaginably light bosons, so wispy that they behave less like billiard balls and more like ripples on a pond. These hypothetical particles, potentially a billion times lighter than electrons, would owe their existence to quantum mechanics. At such tiny masses, they'd exhibit wave-like properties on enormous scales, forming vast interference patterns around galaxies. Picture the halo of the Milky Way not as a swarm of discrete particles, but as a shimmering quantum fog where these waves overlap and swirl. This isn't science fiction. It's a serious attempt to solve one of cosmology's stickiest problems: why small galaxies don't seem to have as much dark matter in their cores as standard models predict. The magic lies in quantum physics. While cold dark matter particles would clump densely at the centers of galaxies, fuzzy dark matter's wave nature prevents this. Quantum mechanics dictates that particles this light can't be squeezed into too small a space. Their wavelengths are simply too large. The result, a natural fluffiness that stops dark matter from over-concentrating, neatly matching observations of dwarf galaxies with their mysteriously diffuse cores. It's as if the universe added a failsafe against cosmic overcrowding. Actions are prime candidates for this role. Originally proposed to solve a puzzle in particle physics, these ultralight particles could pull double duty as fuzzy dark matter. Their wave-like behavior at galactic scales would imprint subtle signatures astronomers are now hunting for. For instance, the distinctive way these waves would bend light around galaxies could create telltale patterns in gravitational lensing observations. Other clues might come from the cosmic microwave background, where fuzzy dark matter's unique fluctuations could leave faint imprints. Critics highlight challenges. If dark matter is this light, wouldn't its waves have prevented small galaxies from forming at all? Simulations suggest otherwise. While fuzzy dark matter suppresses tiny structures early on, it still allows galaxies to emerge, just with sizes that better match what we see. Another puzzle is detection. How do you spot particles so light they barely interact with anything? Innovative experiments using ultra-sensitive magnetic fields or laser arrays aim to catch these whispers of the quantum cosmos. What makes this idea thrilling is its dual elegance. It ties dark matter to fundamental physics while solving observational headaches. Instead of inventing new forces or particles, it simply lets quantum mechanics do the heavy lifting on cosmic scales. Up next, we'll explore an even bolder unification, a mysterious substance that might bridge dark matter and dark energy into a single enigmatic entity. Now let's pivot to a theory that dares to merge two of cosmology's greatest mysteries into one. Imagine if dark matter and dark energy weren't separate entities at all, but different faces of a single enigmatic substance, a dark fluid with properties so bizarre it defies everyday intuition. This is the bold premise of the dark fluid hypothesis, a framework where negative mass, a concept that sounds straight out of science fiction, becomes the key to unlocking cosmic secrets. At its core, dark fluid proposes that the universe's missing mass isn't made of particles or waves, but of an exotic medium with repulsive gravity. Picture a fluid that pushes rather than pulls, where chunks of it would accelerate away from each other, mimicking the effects of dark energy on cosmic scales. Yet, in denser regions like galaxy clusters, this same fluid could clump under its own gravity, behaving like traditional dark matter. It's a cosmic two-for-one deal, elegantly addressing both the universe's accelerating expansion and its structured clumps of matter. Negative mass is the star player here. Unlike ordinary matter, which attracts negative mass would repel other negative masses, a property that could explain why the universe's expansion is speeding up. But here's the twist: when negative and positive masses interact, they create a runaway effect. A negative mass chunk chasing a positive one would perpetually accelerate, never catching up. This bizarre dance might fuel the cosmic acceleration we attribute to dark energy, all while the fluid's denser pockets act as scaffolding for galaxies. Critics raise eyebrows at such a radical idea. Negative mass objects would defy our usual energy conditions, potentially violating cherished physical laws. But proponents counter that the universe isn't obligated to conform to our expectations. Simulations show that a dark fluid with these properties could indeed replicate large-scale cosmic structures while driving expansion, though fine-tuning is required to match observations like the cosmic microwave background. Observational tests are tricky but not impossible. If dark fluid exists, its unique gravitational effects could subtly alter how galaxies move within clusters or how light bends around them. Astronomers might also spot voids, the empty regions between galaxies expanding faster than predicted, a smoking gun for negative mass's repulsive push. What makes dark fluid so compelling is its audacious simplicity. Instead of inventing two unknown components to explain cosmic mysteries, it asks, what if one strange substance could do it all? Whether it holds up under scrutiny or not, it challenges us to rethink gravity, mass, and the very fabric of reality. Next, we'll encounter another rebel idea: particles that change their nature depending on where they are, hiding in plain sight while shaping the cosmos. Now let's turn our attention to a theory that takes cosmic hide and seek to a whole new level. What if the universe's missing mass isn't just invisible? It's actively hiding from us, changing its properties depending on where it is. Enter chameleon particles, a fascinating hypothesis where dark matter isn't just elusive but downright sneaky, adapting to its surroundings like its namesake reptile. At the heart of this idea is a simple but mind-bending concept: particles whose mass isn't fixed. Unlike ordinary matter, which has the same mass whether it's in deep space or a lab on Earth, chameleon particles would shift their weight based on the density of their environment. In empty regions between galaxies, they'd be light and wispy, barely interacting with anything. But in crowded places like galaxy clusters, they'd grow heavier, exerting enough gravitational pull to explain the extra mass we can't see. This adaptability solves a major puzzle in dark matter research. Why haven't we detected it directly in experiments? If dark matter particles are chameleons, they'd become incredibly light, almost undetectable in the high-density environments of Earth-based labs. That would explain why decades of sensitive experiments have come up empty-handed. Out in the cosmos, though, where matter is spread thin, these same particles could dominate gravity's pull, shaping galaxies and clusters just as we observe. The math behind chameleon particles ties into something called scalar fields, which you can think of as invisible energy landscapes filling space. These fields interact with matter in a way that depends on local density, creating the chameleon effect. It's a bit like how a sponge expands in water but shrinks in air, except here, the sponge is a fundamental particle, and the water is the gravitational soup of the universe. Critics point out that chameleon theories require fine-tuning to match all observations. Why, for instance, should particles change mass in just the right way to explain galactic rotations but evade detection? Supporters argue that nature often favors such elegant solutions, pointing to examples like neutrino oscillations, where particles change flavor as they travel. The search for chameleons isn't hopeless. Astronomers could look for subtle distortions in starlight as it passes through regions where these particles should be dense. Lab experiments are also getting clever, using ultra-sensitive devices in low-density environments like underground vacuums to catch chameleons mid-camouflage. What makes this theory so compelling is its audacity. Instead of assuming dark matter is just hard to see, it suggests dark matter is actively avoiding detection, playing by rules we're only beginning to grasp. Whether chameleons are real or not, they remind us that the universe might be far stranger and far sneakier than we ever imagined. Up next, we'll explore another radical idea that turns gravity on its head, suggesting it might not be a fundamental force at all. Now let's shift gears to a theory that flips everything we thought we knew about gravity on its head. What if gravity isn't a fundamental force at all, but something that emerges from the chaos of the quantum world? This is the bold claim made by physicist Eric Verland with his theory of emergent gravity, a radical idea that could rewrite the rules of the cosmos and even do away with dark matter entirely. At its core, emergent gravity suggests that what we perceive as gravity isn't an innate force like electromagnetism, but a side effect of something deeper: quantum entanglement. Imagine the universe as a vast, interconnected web of information. Every particle, every bit of energy is entangled in this cosmic network, and gravity arises naturally from the way this information is organized. It's like how temperature emerges from the random motion of molecules. You can't point to a single molecule and say, "That's temperature," but collectively they create it. Verland argues gravity works the same way, emerging from the underlying quantum buzz of spacetime itself. This idea isn't just philosophical, it offers a concrete solution to the missing mass problem. According to emergent gravity, the extra pull we attribute to dark matter is actually a mismatch in our understanding of how gravity behaves on cosmic scales. In galaxies, for instance, the theory predicts that the way entropy or disorder is distributed across space creates an additional gravitational effect, mimicking the presence of invisible matter. No dark particles needed. The implications are staggering. If gravity emerges from quantum entanglement, then Einstein's geometric view of spacetime might be incomplete. Instead of spacetime curving to create gravity, it's the other way around. Gravity emerges from the quantum relationships between bits of spacetime. This would unify two of physics' greatest mysteries, gravity and quantum mechanics, which have stubbornly resisted reconciliation for over a century. Critics, however, are quick to point out gaps. Emergent gravity struggles to explain all observations, like the precise way galaxies move within clusters, which dark matter handles neatly. And without dark matter, it's unclear how structures in the early universe formed so quickly. Supporters counter that the theory is still young and refinements could close these gaps. After all, Newton's gravity didn't explain Mercury's orbit until Einstein came along. Experiments are starting to test these ideas. Some look for tiny deviations in gravity's strength at microscopic scales where emergent effects might surface. Others study the way galaxies twist light, searching for patterns that match Verlaine's predictions over dark matters. What makes emergent gravity so thrilling is its audacity. It doesn't just tweak our models, it asks us to rethink gravity from the ground up. Whether it's right or wrong, it reminds us that the universe still has profound secrets to reveal. Next, we'll circle back to ordinary matter, exploring whether the missing mass could be hiding in plain sight after all. Now, let's turn our attention to something closer to home: ordinary matter. While exotic particles and radical gravity theories dominate the dark matter debate, could the answer be simpler? Could the universe's missing mass be hiding in plain sight, disguised as everyday matter we just haven't spotted yet? This is the premise of baryonic dark matter, the idea that not all ordinary matter, stuff made of protons, neutrons, and electrons, is glowing brightly in stars or gas clouds. Some of it might be lurking in the shadows, invisible to our telescopes. Take rogue planets, for example. These are planets unbound to any star, drifting through the cold emptiness of interstellar space. Without a sun to illuminate them, they're nearly impossible to see directly. Then there are brown dwarfs, often called failed stars, too massive to be planets but too small to ignite nuclear fusion. These dim objects emit almost no light. Could vast numbers of these dark, frozen bodies account for the missing mass? It's tempting to think so, but the math tells a different story. Even if we tally up every rogue planet, brown dwarf, and other hard-to-detect baryonic objects, they simply don't add up to enough. Observations of the cosmic microwave background, the afterglow of the Big Bang, tell us precisely how much ordinary matter exists in the universe. And when we compare that to what we've actually found glowing in stars, gas, and dust, there's a gap, but it's far too small to explain the 85% of missing mass attributed to dark matter. At best, baryonic dark matter might account for a tiny fraction of the deficit, leaving the vast majority unexplained. This isn't just a numbers problem. The way galaxies rotate and how galaxy clusters behave requires dark matter to be distributed in a very specific way, something ordinary matter, no matter how stealthy, can't replicate. Baryonic matter clumps together, forming dense objects like stars and planets, while dark matter seems to form vast, diffuse halos around galaxies. No population of rogue planets or brown dwarfs could mimic that kind of structure. Still, the search for baryonic dark matter isn't pointless. It's a reminder that the universe still holds surprises, even in the familiar corners of ordinary matter. Projects like microlensing surveys continue to hunt for these dark celestial nomads, peeling back another layer of the cosmic mystery. But for now, the verdict is clear. Baryonic dark matter can't save us from the need for something more exotic. Next, we'll venture into the realm of dark photons, where an invisible force might bridge the gap between the seen and the unseen. Now, let's shift our gaze to something even more elusive, a force that might be weaving the visible and invisible worlds together. Imagine if dark matter wasn't entirely disconnected from our universe but interacted through its own hidden version of light. This is the intriguing possibility of dark photons, hypothetical particles that could mediate a shadowy form of electromagnetism in the dark sector. Unlike ordinary photons, which carry the electromagnetic force we know powering everything from sunlight to radio waves, dark photons would operate in a parallel realm, influencing dark matter particles the way light influences us. The idea here is breathtaking. These invisible carriers could create a subtle bridge between the ordinary matter we see and the dark matter we don't. If dark photons exist, they might occasionally mix with regular photons, leaving faint traces that experiments could detect. Scientists have designed ingenious ways to hunt for these phantom particles. One approach involves high-precision experiments where researchers look for unexpected energy shifts in particle collisions, which could signal a dark photon's fleeting appearance. Another method searches for anomalies in the behavior of electrons, as dark photons might weakly nudge them in ways standard physics can't explain. So far, the results have been tantalizing but inconclusive, hinting at something just beyond our current reach, like whispers in the dark. What makes dark photons especially compelling is their potential to solve multiple puzzles at once. Not only could they explain how dark matter particles interact with each other, but they might also account for other cosmic anomalies, like the mysterious μ1G2 measurement that deviates slightly from theoretical predictions. If dark photons are real, they could be the missing piece connecting these disparate threads. Yet, challenges remain. The strength of this hypothetical dark force is unknown, and the energy range where dark photons might appear is vast. Some models suggest they could be almost weightless, while others propose they're heavier than any particle we've discovered. This uncertainty makes the search like tuning a cosmic radio, slowly scanning through static to find a faint, unfamiliar station. While dark photons remain unconfirmed, their theoretical elegance keeps them at the forefront of dark matter research. They represent a thrilling middle ground, neither entirely separate from our world nor fully part of it, a ghostly handshake between the seen and the unseen. Up next, we'll explore another heavyweight candidate from the realm of supersymmetry, gravitinos, particles that could redefine our understanding of gravity itself. Now, let's turn our attention to a particle that could redefine gravity itself, gravitinos. These elusive heavyweights emerge from the elegant framework of supersymmetry, a theory that proposes every known particle has a hidden, more massive counterpart. Gravitinos are the hypothetical superpartners of gravitons, the yet undiscovered particles believed to transmit gravity. If they exist, gravitinos could be the missing link between gravity and the dark matter puzzle. What makes gravitinos so fascinating is their sheer mass. While most particles we're familiar with, electrons, quarks, even neutrinos, are relatively lightweight, gravitinos could be thousands of times heavier. This heft would make them sluggish in the early universe, causing them to clump together in ways that perfectly mimic the gravitational effects we attribute to dark matter. Picture a cosmic dance where these sluggish giants move just slowly enough to sculpt galaxies into the shapes we observe today. But here's the catch: gravitinos are notoriously hard to detect. Unlike dark photons, which might leave faint traces through their interactions with light, gravitinos barely interact with ordinary matter at all. Their connection to gravity means they'd mostly ignore other forces, passing through planets and stars like ghosts. To spot them, scientists would need instruments sensitive enough to catch the rarest of events, perhaps a gravitino decaying into lighter particles, releasing a burst of energy in a detector buried deep underground. So far, no such signal has been found, but the search continues in labs around the world. One of the biggest challenges is their production. gravitinos would have been forged in the unimaginable heat of the Big Bang, but their abundance depends on how supersymmetry works at those extreme energies. Some models predict too many gravitinos, which would disrupt the delicate balance of elements we see in the cosmos. Others suggest just the right amount to explain dark matter's gravitational grip. It's a tightrope walk between theory and observation, where even small adjustments can tip the scales. Despite these hurdles, gravitinos hold a unique appeal. They offer a way to unify two of physics' greatest mysteries, dark matter and quantum gravity, into a single framework. If supersymmetry is real and gravitinos are out there, they could be the ultimate cosmic missing pieces. For now, they remain shadowy figures on the edge of discovery, waiting for the right experiment to bring them into the light. Up next, we'll meet another relic from the dawn of time, WIMPs, particles so massive they defy conventional detection. Now, imagine stepping into the realm of the unimaginably massive, where particles from the dawn of time defy everything we know about detection. Meet WIMPs, the cosmic heavyweights that make even gravitinos seem lightweight. These theoretical behemoths are relics of the Big Bang, so enormous they dwarf the particles we smash together in today's most powerful colliders. While most dark matter candidates tip the scales at a few hundred or thousand times the mass of a proton, WIMPs could be billions, yes, billions of times heavier. That's like comparing a pebble to Mount Everest. What makes WIMPs so intriguing is their origin story. In the chaos of the early universe, moments after the Big Bang, conditions were so extreme that particles of staggering mass could have formed. Unlike their sleeker cousins, WIMPs wouldn't have been produced in particle collisions, but might instead be remnants of cosmic phase transitions. Think of them as fossils from a time when the universe's energy was unimaginably dense. Their sheer size means they'd move incredibly slowly, almost frozen in place, making them perfect candidates for the gravitational glue holding galaxies together. But here's the twist: their size is also their greatest camouflage. Because WIMPs are so heavy, they'd rarely interact with ordinary matter. You wouldn't find them in a detector buried underground. They'd sail right through it, leaving no trace. Even their name, WIMPs, plays on the irony. WIMP stands for weakly interacting massive particle, but these giants are anything but wimpy. Detecting them would require entirely new approaches, like searching for the faint ripples they'd leave in the fabric of spacetime or the rare high-energy cosmic rays they might emit when they decay. One of the boldest ideas is that WIMPs could be tied to another cosmic mystery: cosmic rays with energies beyond what our physics can explain. Some theorists suggest these ultra-high-energy particles might be the fingerprints of decaying WIMPs, releasing a final burst of power after lurking unseen for billions of years. It's a long shot, but in the hunt for dark matter, no lead is too wild to explore. The challenge, of course, is that WIMPs push our understanding of physics to the brink. If they exist, they'd force us to rewrite the rules of particle production in the early universe. Yet that's exactly why they're so compelling. They represent the edge of what's possible, a frontier where the known laws of physics might break down. For now, WIMPs remain hidden in the shadows, their existence hovering between theory and tantalizing possibility. Up next, we'll delve into an even stranger idea: dark atoms, where invisible particles could be forming their own hidden chemistry in the cosmos. Now consider this: what if dark matter isn't just a sea of solitary particles, but an entire hidden periodic table of its own? This brings us to the fascinating idea of dark atoms, where the universe's missing mass could be tied up in complex, invisible structures. Imagine dark protons and dark electrons coming together just like their ordinary counterparts, but bound by a mysterious dark force. These particles wouldn't interact with light or ordinary matter, but they could form atoms, molecules, even entire dark chemistries lurking right beneath our noses. The concept hinges on a simple but radical idea: dark matter might not be elementary. Instead of single particles like WIMP or actions, it could be built from composite building blocks. Picture a dark proton with a positive charge, not the familiar positive charge we know, but a shadow version governed by a dark electromagnetism. Pair it with a dark electron, and you've got the ingredients for dark hydrogen, the simplest dark atom. From there, the possibilities explode. Dark carbon, dark oxygen, even complex dark organic molecules could exist, invisible to our telescopes but sculpting the cosmos through gravity. Why would dark atoms solve mysteries that simpler theories can't? For one, they could explain why dark matter seems to clump differently at various scales. Ordinary atoms interact through multiple forces: gravity, electromagnetism, the strong nuclear force, creating everything from wispy gas clouds to dense planets. If dark matter has its own forces, its distribution might mirror this complexity. Some galaxies show dark matter halos with puzzling substructure. Dark atoms could naturally account for these nuances, like invisible scaffolding shaping the universe's architecture. But here's where it gets even stranger. Dark atoms might not just mimic ordinary chemistry, they could surpass it. Without the constraints of electromagnetism, dark molecules could form in ways we can't even imagine. A dark version of DNA, a dark crystalline lattice, the rules would be entirely different, dictated by whatever dark forces bind them. Some theorists speculate that dark atoms could even host their own versions of stars or planets, entire dark celestial bodies drifting unseen alongside the visible universe. Detecting dark atoms, though, is a monumental challenge. Since they don't interact with light, we'd need to rely on their gravitational whispers or rare, high-energy collisions. Experiments like the Large Hadron Collider might one day spot anomalies hinting at dark forces, while astrophysical observations could reveal odd gravitational lensing patterns that only dark atoms could explain. It's a needle in a cosmic haystack problem, but the payoff would rewrite our understanding of matter itself. Dark atoms also blur the line between the known and the unknown. If they exist, they'd imply a shadow universe operating in parallel to ours with its own laws and complexities. It's a humbling thought that everything we see, from stars to living cells, might just be one half of a far richer cosmic story. Next up, we'll venture into an even more mind-bending idea: holographic dark matter, where the universe's missing mass might not be physical at all but a projection from the edges of reality. Now, let's take a step into one of the most mind-bending ideas in modern physics: holographic dark matter. Picture this: what if the universe's missing mass isn't made of particles or hidden atoms at all? Instead, it could be nothing more than a cosmic illusion, a projection from the very edges of reality. That's the essence of the holographic principle, a radical theory that suggests our three-dimensional universe might actually be encoded on a two-dimensional surface, like a movie playing on the surface of a vast, unseen screen. The holographic principle flips our understanding of reality on its head. It comes from the study of black holes, where physicists discovered something astonishing. All the information swallowed by a black hole isn't lost inside it, but is somehow preserved on its boundary, the event horizon. This led to the wild idea that the entire universe could work the same way, that everything we see, from stars to galaxies to dark matter, might just be a hologram, a projection of information stored on some distant, higher dimensional boundary. So how does this connect to dark matter? If the universe is a hologram, then dark matter could be an artifact of that projection. Think of it like a shadow cast by information we can't directly access. The gravitational effects we attribute to dark matter might not come from invisible particles, but from the way this cosmic hologram warps and distorts. It's as if the universe has a hidden layer of code, and dark matter is the glitch that reveals its presence. One of the most compelling aspects of this idea is how it could solve some of the lingering puzzles in cosmology. For instance, the way dark matter seems to distribute itself in halos around galaxies fits oddly well with certain holographic models. If gravity itself emerges from quantum interactions on this distant boundary, it could naturally explain why galaxies rotate the way they do. No mysterious particles required. It's a bit like realizing the strange patterns in a video game aren't caused by characters inside the game but by the code running behind the scenes. Of course, the holographic principle isn't without its challenges. For one, it's incredibly hard to test. Unlike dark matter particles, which might leave traces in detectors, a holographic universe doesn't give us much to grab onto. Some researchers are looking for subtle anomalies in the cosmic microwave background or the way black holes behave, hunting for fingerprints of this higher dimensional reality. Others are exploring how quantum entanglement, the bizarre link between particles across vast distances, might be the glue holding the hologram together. What makes this theory so captivating isn't just its potential to explain dark matter, but the way it reshapes our entire view of existence. If the holographic principle is true, then the cosmos is far stranger and more interconnected than we ever imagined. It suggests that what we perceive as solid, separate objects are really just facets of a deeper, unified structure, a cosmic tapestry woven from information itself. Up next, we'll examine another intriguing possibility: neutrino dark matter, where heavier, unseen variants of these ghostly particles might hold the key to the universe's missing mass. Now, let's shift our focus to a ghostly contender in the hunt for dark matter: neutrinos. These elusive particles are already known to zip through the universe, barely interacting with anything, but what if there's more to them than meets the eye? Imagine a heavier, invisible cousin of the neutrino, lurking in the shadows of the cosmos, adding to the universe's missing mass. That's the heart of neutrino dark matter theory, an idea that challenges our understanding of these enigmatic particles. Neutrinos are among the most mysterious particles in the standard model of physics. They're electrically neutral, nearly massless, and pass through matter like ghosts through walls. Every second, trillions of them stream through your body without a trace. For decades, scientists thought they had no mass at all, but experiments eventually revealed they do, just an incredibly tiny amount. This discovery opened the door to a tantalizing question: could there be other types of neutrinos much heavier than the ones we know, hiding in the darkness? Enter sterile neutrinos, hypothetical particles that don't even interact with the weak nuclear force, making them even more elusive than their ordinary counterparts. Unlike regular neutrinos, which occasionally bump into matter, sterile neutrinos would only feel gravity, making them perfect candidates for dark matter. If they exist, they could be drifting through galaxies in vast numbers, their collective gravity shaping the cosmos without ever leaving a detectable signal. One of the strongest hints for sterile neutrinos comes from anomalies in neutrino oscillation experiments, where neutrinos seem to change flavors in ways the standard model can't fully explain. Some physicists argue these odd results point to a fourth, heavier neutrino, one that could account for at least a fraction of dark matter. There's also the intriguing case of certain X-ray emissions from galaxy clusters, which some researchers suggest could be the faint glow of sterile neutrinos decaying into lighter particles. But the idea isn't without its skeptics. If sterile neutrinos are too heavy, they decay too quickly to persist as dark matter. If they're too light, their combined mass wouldn't add up to enough to explain the universe's missing bulk. Finding the right balance is tricky, and so far, no experiment has definitively proven their existence. Projects like the upcoming Deep Underground Neutrino experiment aim to shed light on these mysteries, probing neutrino behavior with unprecedented precision. Even if sterile neutrinos can't fully account for dark matter, they might still play a role in the bigger picture. Their gravitational influence could help explain small-scale quirks in galaxy formation, or they could be part of a mixed dark matter scenario where multiple types of particles contribute to the cosmic mass deficit. What makes this theory so compelling is how it builds on known physics, stretching the boundaries of the standard model without venturing into entirely uncharted territory. As we continue our journey through the cosmos's greatest enigma, the next theory takes us even deeper into the quantum realm, where dark photons, hypothetical carriers of a hidden force, might bridge the gap between the visible and invisible universe. Pivoting from the shadowy realm of neutrinos, let's turn our attention to a theory that reimagines the very fabric of cosmic expansion quintessence. Unlike the static vacuum energy of Einstein's cosmological constant, this idea proposes dark energy as a dynamic, evolving force that could hold the key to the universe's ultimate destiny. Picture a mysterious field permeating space, not unlike the Higgs field, but one that subtly changes over time, alternately pulling the cosmos apart or perhaps even reversing its expansion. That's the essence of quintessence, a theory that challenges our understanding of dark energy's role in shaping reality. At its core, quintessence suggests that dark energy isn't a fixed property of empty space, but a fluid-like field with density and pressure that vary across time and distance. This stands in stark contrast to the traditional view of dark energy as a constant, uniform force, a mathematical fudge factor Einstein once called his greatest blunder. The name quintessence harks back to ancient philosophy, where it referred to a fifth element beyond earth, air, fire, and water. In modern cosmology, it represents a fifth fundamental force, one that could explain why the universe's expansion is speeding up rather than slowing down. What makes this theory so intriguing is its flexibility. Unlike the cosmological constant, which predicts a relentless acceleration leading to a cold, empty, big freeze, quintessence allows for scenarios where dark energy's influence waxes or wanes. In some models, the field could eventually dissipate, allowing gravity to regain dominance and pull the universe back into a big crunch. Others suggest it might grow stronger, tearing apart galaxies, stars, and even atoms in a catastrophic big rip. This spectrum of possibilities hinges on the field's hypothetical equation of state, a measure of how its pressure relates to its energy density. Observational clues for quintessence come from subtle discrepancies in measurements of the universe's expansion rate. While the cosmological constant fits much of the data, some studies of distant supernova and galaxy clusters hint that dark energy's strength might not be perfectly uniform. For instance, the Dark Energy Survey has found tentative evidence that the acceleration rate could vary slightly over cosmic time, a potential fingerprint of quintessence. Yet these signals remain controversial, buried in the noise of observational uncertainties. Critics argue that quintessence introduces unnecessary complexity when simpler explanations suffice. Without direct detection of the field or its hypothetical particles dubbed quintessence, the theory leans heavily on mathematical elegance rather than empirical proof. It also struggles to explain why the field's energy density is so finely tuned to match matter's density at precisely this moment in cosmic history, a coincidence known as the "why now?" problem. Despite these hurdles, quintessence keeps physicists pondering. It offers a narrative where dark energy isn't an immutable fate but an active player in the universe's story, with twists still unwritten. Upcoming telescopes like the Vera Rubin Observatory could tilt the scales by delivering sharper measurements of cosmic acceleration, either cornering quintessence or consigning it to history. As we peer into the cosmos's uncertain future, the next theory ventures even further into the speculative phantom energy, a dark energy variant so extreme it could rip spacetime itself apart. Now, let's take a step into the far edges of cosmic theory, where dark energy doesn't just accelerate the universe's expansion, it obliterates it. Phantom energy is the nightmare scenario of cosmology, a runaway version of dark energy so potent it could tear the fabric of spacetime apart in a cataclysmic event known as the Big Rip. Unlike quintessence, which leaves room for cosmic uncertainty, phantom energy has a singular, violent destiny in mind. The concept hinges on a simple but terrifying idea. What if dark energy's strength isn't just constant or slowly changing, but growing infinitely over time? In this model, the equation of state, the relationship between dark energy's pressure and density, crosses a critical threshold. Instead of counteracting gravity, phantom energy's negative pressure becomes so extreme that it overwhelms every binding force in the universe. Picture a balloon inflating faster and faster until its rubber stretches too thin and pops. Now imagine that balloon is reality itself. Here's how the big rip unfolds. First, the accelerating expansion shreds the cosmic web, ripping galaxy clusters apart. Next, individual galaxies are torn asunder, their stars flung into the void. As the phantom field intensifies, solar systems disintegrate, planets are ripped from their orbits, and eventually, even atoms and subatomic particles are pulled apart. The final moments would see space-time itself rupturing at the quantum level, leaving behind a chaotic, fragmented nothingness. It's a far cry from the gradual fade of the Big Freeze or the cyclical collapse of the Big Crunch. This is annihilation on the most fundamental scale. What's eerie is that phantom energy isn't purely speculative math. Observations of distant supernova and baryonic acoustic oscillations have tentatively allowed for equations of state that dip below the critical threshold, though the evidence remains ambiguous. The key mystery lies in whether dark energy's pressure-to-density ratio, denoted by the parameter W, could be less than -1, a value that would signal phantom behavior. Some modified gravity theories and string theory models even provide frameworks where such energy could arise naturally, albeit under exotic conditions. Critics, of course, highlight the theory's apocalyptic implications as a red flag. If phantom energy were real, it would raise unsettling questions about why the universe's parameters are fine-tuned to allow for such a violent end. There's also the problem of causality. In a phantom-dominated cosmos, the accelerating expansion could eventually outpace light itself, creating horizons where no signals or interactions can propagate. Communication between particles and even the laws of physics would break down long before the final rip. Yet phantom energy's value lies in its ability to stretch our understanding of dark energy's extremes. It forces us to confront the limits of cosmological models and ask whether the universe's fate is truly as serene as a slow freeze or as dramatic as a crunch. Future projects like the European Space Agency's Euclid mission aim to measure dark energy's equation of state with unprecedented precision, potentially ruling out or validating this grim possibility. As we grapple with these existential forecasts, our next theory offers a gentler alternative, blending dark matter and dark energy into a single, elegant solution: the Chaplygin gas. Stepping away from the cataclysmic visions of phantom energy, we arrive at a theory that seeks harmony rather than destruction. The Chaplygin gas offers an elegant solution to two of cosmology's greatest puzzles, dark matter and dark energy, by weaving them into a single, exotic substance. Imagine a cosmic fluid that starts its life behaving like ordinary matter, clumping together to form galaxies, only to later transform into a smooth, repulsive force driving the universe's expansion. This is the dual nature of the Chaplygin gas, a hypothetical medium that could simplify our understanding of the cosmos. The theory takes its name from a concept in aerodynamics, but its cosmological version is far more revolutionary. Unlike traditional models that treat dark matter and dark energy as separate entities, the Chaplygin gas unifies them through a unique property. Its pressure is inversely proportional to its density. In the early universe, when matter was densely packed, this fluid would have acted like cold dark matter, providing the gravitational scaffolding for galaxies to form. But as the universe expanded and the gas thinned out, its pressure would drop, causing it to behave more like dark energy, accelerating cosmic expansion. One substance, two roles, a cosmic chameleon adapting to the needs of the universe. What makes this idea so compelling is its mathematical elegance. The equation describing the Chaplygin gas is strikingly simple, yet it captures the transition from a matter-dominated era to an energy-dominated one without requiring ad hoc assumptions. Observations of large-scale structure and supernova data fit surprisingly well with this model, avoiding some of the fine-tuning problems that plague other theories. For instance, it naturally explains why dark energy's influence became noticeable only recently in cosmic history, a coincidence that puzzles physicists in standard models. Critics, however, point to challenges. The Chaplygin gas struggles to replicate the precise details of galaxy rotation curves, where dark matter's gravitational effects are most pronounced. There's also the question of how such a fluid could arise in nature. Some proposals tie it to string theory or brane cosmology, suggesting it might emerge from higher dimensional physics. Others argue that its behavior is too idealized, lacking the granularity needed to match all observational data. Yet the theory's potential rewards are too significant to ignore. If the Chaplygin gas is real, it would mean that 85% of the universe's content isn't just invisible. It's a single, dynamic entity evolving alongside the cosmos. Future telescopes like the Vera Rubin Observatory could test this by mapping the universe's expansion history with finer precision, searching for telltale signs of this unifying fluid. From the violent extremes of phantom energy to the graceful unity of the Chaplygin gas, our journey through dark energy theories reveals a cosmos far stranger than we once imagined. Next, we'll challenge Einstein's greatest legacy by asking whether gravity itself might be the culprit behind the missing mass. Now let's shift our gaze from cosmic fluids to the very fabric of gravity itself. What if the missing mass isn't hiding in some exotic particle or unseen dimension, but in the laws that govern the universe? Variable gravity theories dare to question Einstein's foundational assumption that gravity's strength is constant across space and time. Imagine a cosmos where gravity weakens as galaxies drift apart or strengthens in the voids between them. This isn't science fiction, it's a radical rethinking of how gravity might work on the grandest scales. The seeds of this idea trace back to pioneering work by physicists like Mordechai Milgrom, whose modified Newtonian Dynamics, or MOND, first suggested that gravity behaves differently at low accelerations. But variable gravity theories take this further, proposing that even Einstein's relativity might need tweaking. Instead of invoking dark matter to explain why galaxies rotate faster than expected, these theories suggest that gravity itself becomes stronger in regions where conventional physics predicts it should fade. Picture a rubber band that stretches unpredictably, sometimes stiff, sometimes slack depending on where and when you pull it. That's the kind of flexibility some theorists now attribute to gravity. Supporters argue this approach solves multiple puzzles at once. For instance, it could explain the bullet cluster, where two colliding galaxy clusters seem to have their mass separated from their visible matter, a phenomenon often cited as proof of dark matter. Variable gravity models propose that the cluster's gravity might have been temporarily amplified during the violent collision, creating the illusion of invisible mass. Similarly, the accelerating expansion of the universe, usually credited to dark energy, might simply reflect gravity growing weaker over cosmic time. Yet challenges remain. Adjusting gravity's strength risks breaking well-tested predictions like the precise orbits of planets in our solar system. To avoid this, theorists craft screening mechanisms, mathematical tricks that ensure gravity behaves normally in regions we've measured carefully, like Earth's neighborhood, while allowing it to change in the distant cosmos. It's a delicate balancing act, and not all physicists are convinced. Critics point to the elaborate fine-tuning required, asking whether inventing new gravity laws is any simpler than hypothesizing dark matter. Experiments are now putting these ideas to the test. Gravitational wave detectors like LIGO could reveal subtle changes in gravity's behavior over vast distances. Meanwhile, surveys mapping the universe's large-scale structure might uncover patterns that defy Einstein's predictions. If gravity does vary, the implications will be profound not just for cosmology, but for our understanding of fundamental physics. From unifying fluids to bending the rules of gravity, our hunt for the missing mass keeps rewriting the cosmic playbook. Up next, we'll explore another relic of the early universe, cosmic strings, and their potential role in this grand mystery. Now let's unravel another cosmic curiosity: strings, but not the kind you tie. Cosmic strings are theoretical cracks in the fabric of spacetime, thought to have formed in the universe's fiery infancy. Picture the early cosmos as a cooling pot of molten glass. As it solidified, tiny fractures might have appeared, threads of pure energy thinner than an atom but stretching across billions of light years. These cosmic strings, if they exist, could be the universe's hidden scaffolding, warping gravity around them in ways that might explain some of its missing mass. The idea stems from phase transitions in the early universe, moments when the fundamental forces split apart as temperatures dropped. Just as ice crystals form jagged lines when water freezes, these transitions could have left behind one-dimensional defects: cosmic strings. Unlike black holes or stars, they wouldn't be made of matter but of trapped energy, dense enough to bend spacetime like a bowling ball on a trampoline. This curvature could mimic the gravitational pull of unseen mass, acting as invisible lenses that distort the light of distant galaxies. Some models suggest these strings might also have seeded the cosmic web. As they vibrated or snapped, they could have sent shock waves through the primordial plasma, nudging matter into the clusters and filaments we see today. Imagine plucking a guitar string and watching the vibrations ripple through smoke. That's how cosmic strings might have sculpted the universe's large-scale structure. Remarkably, their gravitational fingerprints could linger in subtle patterns in the cosmic microwave background, the afterglow of the Big Bang. Yet detecting these elusive threads is a challenge. Unlike dark matter particles, cosmic strings wouldn't interact with light or matter at all. Instead, astronomers hunt for their secondary effects, like double images of the same galaxy created by a string's lensing, or abrupt jumps in the cosmic microwave background's temperature. A tantalizing hint came in 2020 when a team analyzing quasar light reported anomalies consistent with a string's wake, though the evidence remains debated. Critics argue that even if cosmic strings exist, their total mass might be too small to account for all the missing matter. But proponents counter that a network of strings woven through the cosmos could collectively exert enough gravitational influence to tip the scales. Others speculate these strings might decay over time, releasing bursts of gravitational waves that detectors like LIGO could one day catch. Whether as gravitational lenses, cosmic architects, or dark matter contenders, cosmic strings remind us that the universe's secrets might be hidden in its very geometry. Up next, we'll consider an even more fleeting possibility. What if dark matter isn't eternal but slowly fading away? Now let's shift our gaze to a quieter, more gradual possibility. What if dark matter isn't as permanent as we think? Picture a cosmic hourglass, its grains of sand slipping away one by one. In this scenario, dark matter particles might be doing something similar, slowly decaying over eons into lighter, more elusive forms. This idea, known as dark matter decay, suggests that the universe's missing mass isn't just hidden, it's fading, transforming into something else entirely. At the heart of this theory lies a simple but profound question. Could dark matter have a half-life? Just as radioactive elements like uranium break down over time, dark matter particles might undergo their own form of decay, splitting into lighter particles or even pure energy. These decay products could be nearly undetectable, perhaps neutrinos or photons with wavelengths too faint for our telescopes to catch. But their collective effects might subtly alter the behavior of galaxies, offering clues to their existence. One way this decay could manifest is in the way galaxies rotate. if dark matter particles are vanishing, their gravitational grip on stars and gas would weaken over time. Imagine a spinning ice skater gradually extending their arms. The rotation slows as the mass distribution changes. Similarly, galaxies with decaying dark matter might exhibit unexpected patterns in their rotation curves, deviating from the predictions of stable dark matter models. Astronomers have already noted peculiarities in some galactic motions that could align with this idea, though alternative explanations remain on the table. Another tantalizing hint comes from cosmic rays, high-energy particles streaming through space. If dark matter decays into lighter particles, those products could collide with interstellar gas, producing faint bursts of radiation. Telescopes like the Fermi Gamma Ray Space Telescope have scoured the sky for such signals, particularly from dense regions like galaxy clusters where dark matter should be abundant. A few unexplained gamma-ray excesses have sparked excitement, though skeptics point to more mundane sources like pulsars as the likely culprits. Critics of the decay theory raise a key challenge. If dark matter is disappearing, why hasn't the universe's structure crumbled more noticeably? After all, dark matter is the cosmic glue holding galaxies and clusters together. Proponents counter that the decay could be achingly slow, stretching over billions of years, far longer than human observations. Alternatively, the decay products themselves might still exert gravitational influence, softening the impact on galactic dynamics, the most intriguing possibility. Dark matter decay could help explain why the universe's expansion is accelerating. If decaying particles release energy, that energy might act as a kind of fuel for dark energy, subtly pushing galaxies apart. It's a cosmic balancing act. As dark matter fades, its transformation could be driving the very acceleration that puzzles astronomers today. While the evidence remains circumstantial, the hunt for decaying dark matter is far from over. Next-generation experiments like the Vera Rubin Observatory could spot finer anomalies in galactic behavior, while underground detectors might catch the faint whispers of decay products. Whether this theory holds up or not, it reminds us that the universe's mysteries might not just lie in what's hidden, but in what's quietly, persistently changing. Up next, we'll venture into another shadowy corner of physics, a hidden valley of particles that might hold the key to dark matter's secrets. Now let's step into a realm where the ordinary rules of particle physics might not apply, a hidden valley secluded from our familiar universe. This isn't science fiction, it's a serious hypothesis suggesting an entire sector of particles exists, barely interacting with the matter we know. These so-called hidden valley models propose that dark matter could be part of this shadowy family, quietly influencing the cosmos while remaining almost entirely invisible to us. The idea hinges on a simple but radical premise. What if the particles making up dark matter aren't just hard to detect because they're elusive, but because they belong to a separate valley of reality? In this scenario, these hidden particles would have their own forces, interactions, and even their own version of chemistry, entirely distinct from the protons, neutrons, and electrons we're made of. The only bridge between their world and ours, gravity, and perhaps the faintest whisper of other feeble forces. One compelling candidate from this hidden valley is the dark photon, a hypothetical particle that could mediate a dark form of electromagnetism. Just as photons carry the electromagnetic force in our universe, dark photons might facilitate interactions between dark matter particles. But here's the twist. If dark photons occasionally mix with regular photons, they could create a tiny, detectable signal, like a faint radio transmission bleeding through from another channel. Experiments like the Large Hadron Collider and specialized dark matter detectors are actively searching for these elusive whispers. Another intriguing possibility is that the hidden valley isn't just a single particle but an entire spectrum, much like our own standard model. There could be dark protons, dark electrons, even dark atoms forming complex structures we can't see. Some theories suggest these dark atoms might clump into invisible galaxies or stars, mirroring the visible universe in ways we're only beginning to imagine. If true, this would mean the cosmos is far richer and far stranger than we've ever suspected. Critics, of course, question how we'd ever confirm such a hidden realm. Without stronger interactions, how do we prove it's there? Proponents point to subtle anomalies in particle collisions or cosmic ray data that don't fit the standard model. For instance, if a particle accelerator produces unexpected energy imbalances, it could hint at energy leaking into the hidden sector. Similarly, certain astrophysical phenomena, like the unexplained cooling of some neutron stars, might be explained by dark photons carrying heat away into the valley. The hidden valley idea also offers a tantalizing solution to one of dark matter's biggest puzzles. Why hasn't it clumped more densely around galaxies? If dark matter particles interact through their own forces, these interactions could generate pressure, preventing them from collapsing into overly dense regions, much like how ordinary gas resists compression. This would neatly explain why dark matter halos around galaxies appear smoother and more diffuse than some simulations predict. What makes this theory so fascinating is its potential to unify multiple cosmic mysteries. Beyond dark matter, hidden valley particles might explain other gaps in physics, like the nature of neutrino masses or the hierarchy problem in particle physics. It's a reminder that the universe's secrets might not lie in tweaking what we know, but in discovering entirely new layers of reality. Up next, we'll turn to another bold idea, technicolor, a theory where dark matter emerges from forces even more powerful than the ones binding our atoms. Now let's shift our focus to a theory that takes inspiration from one of the most powerful forces in nature, the strong nuclear force. Imagine a world where dark matter isn't made of fundamental particles at all, but instead arises from interactions even more intense than those binding atomic nuclei. This is the heart of technicolor theory, a bold framework that suggests dark matter could be a byproduct of a hidden, ultra-strong force. At its core, technicolor proposes an analogy to the strong force we already know, which holds quarks together inside protons and neutrons. But here's the twist. Instead of quarks, this new force binds technoquarks, hypothetical particles that could form composite dark matter, much like how protons are composite particles of quarks. These technicolor particles wouldn't just be heavier versions of familiar matter. They'd emerge from a completely separate sector of physics, governed by rules far more extreme than anything in our standard model. One compelling aspect of this idea is how it tackles multiple puzzles at once. For instance, the hierarchy problem, the puzzling question of why the Higgs boson is so lightweight compared to the immense energy scales of gravity, finds a potential solution here. Technicolor theories suggest that the Higgs itself might not be a fundamental particle, but a composite one arising from the interactions of technoquarks. This would mean the Higgs is more like a ripple in a deeper, invisible force field rather than an elementary particle. But where does dark matter come in? If technoquarks exist, they could form stable, neutral composites, technobaryons, that behave just like the dark matter we've been searching for. These particles would be massive, weakly interacting, and abundant enough to account for the universe's missing mass. Unlike traditional WIMP, which are often imagined as single, fundamental particles, technobaryons would be complex objects with internal structure, offering a richer set of behaviors and potential detection signatures. Experiments are already hunting for hints of this hidden sector. Particle colliders like the Large Hadron Collider might produce technicolor particles in high-energy collisions, leaving behind telltale patterns of missing energy or unusual jets of particles. Meanwhile, astrophysical observations could provide indirect clues. For example, if dark matter annihilations produce gamma rays with specific energies, it might point to the decay of technicolor composites rather than simpler particles. Critics, of course, point out the challenges. Technicolor theories often require fine-tuning to match observed phenomena, and no direct evidence has been found yet. But proponents argue that the absence of clear signals might simply mean we haven't probed the right energy scales or looked for the right patterns. The history of physics is full of surprises after all. The neutron was once just a theoretical placeholder until experiments caught up. What makes Technicolor so fascinating is its audacity. It doesn't just tweak existing models, it proposes an entirely new framework that could explain dark matter, the Higgs mechanism, and even the origins of mass itself. If correct, it would mean that the universe's hidden bulk isn't just made of unseen particles, it's built from unseen forces, operating in realms of energy we've only begun to imagine. Up next, we'll explore an idea that ties the cosmos's missing mass to the very fabric of space itself, vacuum energy, and the enduring mystery of the cosmological constant. Now, let's turn to a concept that challenges our very understanding of nothingness. What if the universe's missing mass isn't hiding in exotic particles or hidden forces, but is instead woven into the fabric of empty space? This is the essence of vacuum energy, a radical reinterpretation of dark energy that suggests the cosmos is being pushed apart by the innate energy of the void itself. At first glance, the idea seems almost paradoxical. How can empty space, a true vacuum, contain energy? Quantum physics reveals that even in a perfect vacuum, particles flicker in and out of existence due to quantum fluctuations. These fleeting disturbances generate a baseline energy known as zero-point energy, a faint but persistent hum in the cosmos. If this energy permeates all of space, it could act as a repulsive force, accelerating the universe's expansion, exactly what we observe with dark energy. The appeal of this theory lies in its simplicity. Unlike Technicolor or supersymmetry, it doesn't require inventing new particles or forces. Instead, it repurposes a well-established quantum phenomenon to explain one of cosmology's greatest puzzles. But here's the catch. When physicists calculate the predicted strength of vacuum energy, the numbers are catastrophically wrong. The theoretical value is around 120 orders of magnitude larger than what we actually observe. This staggering mismatch is called the cosmological constant problem, and it remains one of the most embarrassing unsolved problems in modern physics. Why does this discrepancy exist? Some theorists argue that our understanding of quantum fields is incomplete, or that unknown symmetries cancel out most of the vacuum's energy. Others propose that multiple universes with different vacuum energies exist, and we happen to reside in one with an improbably small value, a controversial idea tied to the multiverse hypothesis. Regardless, the gap between prediction and observation suggests that vacuum energy, if it's the answer to dark energy, operates in ways we don't yet grasp. Despite these challenges, vacuum energy still holds tantalizing clues. For instance, its uniform distribution would explain why dark energy's effects only become noticeable on cosmic scales, where the cumulative push of countless tiny fluctuations overwhelms gravity. It also aligns with Einstein's cosmological constant, a term he initially added to his equations to keep the universe static, only to later dismiss it as his greatest blunder. Ironically, that very term might describe the accelerating expansion he never lived to see confirmed. Current experiments can't directly measure zero-point energy's gravitational impact, but they're narrowing down the properties of dark energy. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope map the universe's expansion with unprecedented precision, searching for deviations that might hint at vacuum energy's true nature. Meanwhile, advances in quantum gravity theories like string theory or loop quantum gravity could someday reconcile the cosmological constant problem by revealing deeper layers of reality. Vacuum energy forces us to confront the limits of our knowledge. It's a reminder that sometimes the most profound mysteries aren't about what's hidden in the cosmos, but what's hiding in plain sight. the invisible energy of empty space itself. Up next, we'll venture into one of the most provocative ideas on our list, the possibility that the universe's missing mass isn't physical at all, but a glitch in the code of reality itself. Now, let's take a step into the realm of the extraordinary. What if the universe's missing mass isn't a physical substance at all, but something far more mind-bending? Imagine for a moment that our entire reality, every galaxy, every particle, even the very laws of physics, is nothing more than an intricate simulation running on some unfathomably advanced computer. This is the simulation hypothesis, and it offers a radical explanation for the mystery of dark matter and dark energy. They might simply be glitches or shortcuts in the code of our simulated universe. The idea isn't as far-fetched as it sounds. Think of how video games handle processing power. To save resources, game engines often render only what the player can see, leaving distant objects as low-detail approximations. Now scale that up to a universe-sized simulation. Dark matter's gravitational effects could be the program's way of simplifying calculations in regions it doesn't fully render, while dark energy might be an algorithmic tweak to ensure the simulation runs smoothly over cosmic timescales. Even the bizarre behavior of quantum particles, like existing in multiple states until observed, could be explained as processing optimizations where the simulation only resolves details when necessary. Philosophers like Nick Bostrom have argued that if civilizations can create simulations indistinguishable from reality, the odds are high we're living in one. After all, there might be countless simulated universes for every real one. Physicists have even proposed ways to test the hypothesis, like searching for pixelation in the fabric of spacetime or anomalies in high-energy particle collisions that reveal underlying computational limits. So far, no such evidence has been found, but the search continues. Skeptics dismiss this as pure speculation, and they're not wrong. There's no direct proof. Yet the simulation hypothesis forces us to question fundamental assumptions. If the universe is code, then dark matter and energy might not be things to discover, but artifacts of how reality is programmed. It's a modern twist on ancient philosophical questions. What is real? And if our cosmos is a construct, what does that say about the nature of existence itself? As we wrap up our journey through these 30 theories, remember this: the mystery of the universe's missing mass isn't just about physics. It's a puzzle that stretches from the quantum world to the cosmic horizon, challenging us to rethink everything we know about space, time, and reality. Whether the answer lies in undiscovered particles, hidden dimensions, or even lines of alien code, one thing is certain: the truth, when we find it, will be stranger than fiction. If you've enjoyed this cosmic deep dive, don't forget to hit that like button and subscribe for more mind-expanding explorations. The universe is full of mysteries, and together we'll keep uncovering them one theory at a time. As we reach the end of our journey through the enigmatic missing mass of the universe, let's take a moment to reflect on just how many possibilities lie before us. From the invisible grip of cold dark matter to the mind-bending implications of the simulation hypothesis, we've explored a breathtaking spectrum of ideas, each one pushing the boundaries of what we think we know. Some theories, like WIMP and actions, lean on the cutting edge of particle physics, while others, like emergent gravity and dark fluid, challenge the very foundations of Einstein's relativity. And then there are the wild cards: primordial black holes, mirror matter, even the holographic universe, each offering a radically different lens through which to view the cosmos. What's truly remarkable is how this mystery connects so many seemingly unrelated fields. Astronomers, particle physicists, mathematicians, even philosophers have all thrown their hats into the ring, proving that the question of missing mass isn't just about filling a gap in our equations. It's about understanding the fundamental nature of reality, and here's the humbling part: despite decades of research, we still don't have a definitive answer. The universe, it seems, is keeping its secrets close. So where does that leave us? With curiosity, of course. Maybe one of these theories resonated with you. Perhaps you're drawn to the elegance of supersymmetry or the audacity of Kaluza-Klein extra dimensions. Or maybe you've got a theory of your own. That's the beauty of science. It's a conversation, not a monologue. And that's where you come in. Drop a comment below, tell us which idea captivates you most, or share a cosmic question you'd love us to explore next. If this deep dive into the universe's hidden layers left you hungry for more, don't forget to hit that subscribe button and ring the notification bell. There are countless mysteries waiting to be unraveled, from the nature of black holes to the fate of the cosmos itself. Together, we'll keep peeling back the layers of reality, one mind-expanding theory at a time. Until next time, keep looking up and keep wondering. The universe isn't done surprising us